It's time to turn our attention to the divide blower door air change rate by X, usual suspects. Measuring airflows in buildings is a hassle, and it can take considerable resources. Evidence is scarce, and what little exists has gradually worked its way into the hive mind of the building science community, and it's lodged in lots of different dusty corners. And of course, details and assumptions, they've gotten lost in translation on the way into that hive mind, and so concepts get used in ways that the originators might find surprising. And sometimes, when there are limited resources to tackle an issue at a fundamental level, the hive mind remembers one of its dusty corners. And a bit of the dust is brushed off, and it gets plugged into the various backroom processes and decision-making rules. Periodically, someone digs a bit, finds some aspect that's a bit tenuous or worse, and suggests an alternative convention. So, suspect 1, the divide the 50 Pascal flow by 20 rule. Suspect 1 is a convention that assumes long-term infiltration rates can be estimated as a fraction of a blower door test value. There's lots and lots of scope for this rather convenient placeholder in compliance regimes, and especially in these times of limited resources. I found a couple of examples of group investigating Suspect 1. A paper in Energy Buildings from 2020 compares the divide by convention with tracer gas measurements in a score of residences in the East Midlands of the UK. The paper found a considerable gap in how compliance tools treated facade leakage and what the measurements were suggesting. The residences were a mix of construction types and ages from about 1900 to 2012. And the blower door test air change rates went from 4.13 at best to 14.97. If we would take the divide by 20 convention, it would yield infiltration rates between 0.02 and 0.74. My observation on this paper is that the building science community still does not measure enough and for long enough and on an ongoing basis to inform decision makers. There have been incremental improvements in construction since 2012, and it would be really great if a new round of observations could be taken so there was some new information to feed into the hive mind. I'm not holding my breath. Another bit of digging is a source for a 2025 report looking at updating the methodologies for estimating infiltration rates in the UK SAP method. My take on this report is that the hive mind forgot the convention was low precision. The thing is, the alternatives that were considered were, in general, restricted still to single zone treatments of a building, and they really only lightly touched on the possibilities of numerical assessments to help out. On a side note, my group did scores of numerical simulations supporting the development of the UK housing energy model, and we found multi-zone approaches far superior to single-zone approaches. I hold a belief that we should let numerical tools do the heavy lifting. So, let's see what that gets us in comparison with fixing infiltration based on some variant of the divide by convention. A reasonable first question, is that convention applicable when we've got tighter than best practice building blower door tests? My prior video introduced calibrated orifices around a facade based on a 1.2 air changes at 50 pascals flow test. It was in the context of a 4-room test building. This flow rate is better than the tests mentioned earlier, but it's also not nearly up to the scratch of what's required in Passive House. Dividing 1.2 air changes by 20 gives 0.06 air changes. That seems to me to be a seriously small number. If we use 2.5 liters per second per person to limit CO2 risk, goodness, we're falling short. And yet, newspapers, they're not full of death notices. A second reality check. Remember the slide from the prior video suggesting that at a permeability of 1, which is kind of like Passive House, is equivalent to a 5p coin-sized hole drilled in each 5 square meter section of the building envelope. Well, for our 4-room building, that's 55 pence holes. In the prior video about the impact of changing wind exposure, there were clearly multiple sets of performance. Let's go over the annual headline numbers from the wind exposure study. Okay, site changes, they minimally influence the annual extremes in dry bulb resultant temperatures. Site changes also minimally influence the peak cooling capacity or the hours that cooling is needed. The annual gains and losses via facade leakage were equivalent to, say, 200 kilowatt hours for a city center site, up to 500 kilowatt hours for an open countryside site. The annual demands for heating range from 190 kilowatt hours for the city center to 300 kilowatt hours in the open countryside. The annual demands for cooling from 1100 kilowatt hours for the city center to 975 for the open countryside. Those were the annual numbers. If we look at a May week, when the wind speeds are typically quite low, the annual pattern for infiltration influence, well, that's mostly the same. And changes in the energy impact on air movement roughly reflected the difference in cooling demand over time. If, however, we look at a windy January week, the annual pattern, well, that's not really evident. Changes in wind exposure have a considerable impact on heating capacity and on heating demand over time, and on the number of hours heating is needed. Two takeaways from this. If one were to define a divide by that gave a fair match to the dynamic infiltration assessments for one of the site types on an annual basis, it probably wouldn't be very representative during windy winter conditions. And given the range of dynamic performance predictions in the tables we just saw, stands to reason that for those who insist on using a divide by convention, there's no single divisor workable for all sites. To test these ideas, we need to run quite a few fixed flow variants, create a reasonable performance matrix to compare within. Here are the different flow rates I ended up running. Here's a table with the headline values for each of the annual assessments. As was the case with the exposure study, different infiltration rates do not do much about temperatures in the buildings at the extremes. The energy impact of air movement through the facade, wow, that increases from, say, 187 to 536 kilowatt hours across that range. Capacity for heating and cooling don't change very much across the range. Heating demands over time range from 178 to 290 as the fixed rate increases. The hours heating is required also creeps up. But cooling demand over time and the hours that's required doesn't really change much. If we look at the May not very windy week, we see a tight range for most of the metrics across the range. However, the windy week in January with various fixed infiltration rates shows a gradual transition in each of the metrics. This gradual change is much less than what was observed during the dynamic assessment. So, which suspect matches an urban location? Let's start with a comparison of the calibrated orifice for an urban wind exposure against the nearest divide by conventions. The annual headline numbers for divide by 15 are probably the closest for this wind exposure. Energy impact of infiltration is close, as are its cooling capacity and cooling demand. There's a lesser match for heating capacity, heating demand over time, and the hours heating is needed. How's that so? Well, let's drill down, and the peak energy impact of infiltration certainly differs. And there are, however, minor differences in capacity. The energy demand over time differs slightly room by room. The room energy balance shows the orifice approaches slightly higher losses. If we look at the May not windy week, we get similar sorts of numbers. And if we drill down to the energy impact of facade airflows, we see little windward or leeward impact on the rooms. If we look at the resultant temperatures in the rooms and the heating injections and infiltration, the pattern is similar. The differences introduced by the greater infiltration on the left does not really show up in the other lines of the graph. Turning to a windy January week, the closest match turns out to be, divide by 8. Several of the metrics are close, and it's worth drilling down a bit. The energy impact of air through the facade shows a very different pattern, and this impacts the heating demands that week as well. The wind this week is mostly from the south, and there's a clear windward-leeward effect. If we look at the energy demand over time, more heating is needed in the south rooms. And in the box A, the energy balance of infiltration flips from being a big number to just being a bit of noise. If we graph performance, it's easier to see that the heating demands differ in magnitude and duration. What might we take away from this comparison of an urban context? Well, many of the headline values are in agreement, especially over the long term. Accountants will be pleased. However, when we focus on a windy winter week, a different story emerges. Now, whether these differences might lead to different design decisions, that's debatable. Certainly the numbers point to windward versus leeward patterns that call into question the basic assumption that infiltration is evenly distributed in a building. Which suspect matches an open countryside with some sheltering? One of the scenarios in the orifice study was to take an open countryside site and shelter it on one side. And some empirical methods allow for local sheltering. So how might that play out with a divide by convention? Looking at the annual headline numbers, there's a closer fit with divide by 10 convention, but heating is actually a better match with divide by 9 convention. Heating capacity is under-predicted in the divide by conventions tested. If we look at the mostly calm May week, there are quite a few similarities. But if we look at the windy week, none of the tested divide by conventions are close. Heating capacity, demand over time, and hours heating is required. They're all undercounted. Which suspect matches open countryside? Well, taking away the sheltering increases the exposure, and the headline numbers point to rather divide by 9. And again, heating capacity, heating demand over time are underpredicted in any of the divide by conventions I tested. If we look at the mostly calm May, there are, yes, quite a few similarities. But the winter week, nothing tested in a divide by conventions are vaguely close. Again, heating capacity, demand over time, and hours required are all undercounted. But the process gets seriously tenuous when dealing with windy winter conditions. So relying on a divide for by winter adds risk to the provision of heating and the running costs of heating. So what happens if the comparison is with what most people would consider the most sheltered position, that of a city center location? Well, the annual headline numbers for divide by 20 are in line with the city center wind exposure, although heating capacity is somewhat of an outlier. Let's drill down to the raw report and see the differences over the year. Well, they're reasonably constrained differences. Looking at the heating and cooling demand over the all match is slightly less good at an individual room level. The annual energy balance for the front left room is eerily similar with the orifice and with the fixed. If we look at the May not windy week, there's a reasonably close match to the divide by 20 convention. Now, drum roll, what about the windy January week? Well, when we look, the possible matches are all over the place. Let's drill down a bit and look at the monthly energy impact of infiltration. On the left is the infiltration values. Well, they're greater magnitude and they dance around a lot more than the columns on the right. The rooms which were on the leeward side, such as Box C, had little orifice-based infiltration in some months. If we look at the windy January week, the energy impact of infiltration is vastly more in the case of the orifice-based assessment, and the heating demand reflects this. And for the energy balance for the front left room, the total gains and losses are greater for the orifice assessment. For the city center site, the May performance is actually quite similar of the annual. So the annual headline rates, which the box tickers will notice, is complicated by windy weather periods which show a different pattern. Indeed, there were differences in each month at the room level due to windward and leeward effects. In summary, on the question about whether a divide by convention was even applicable to buildings with blower door test values approaching word air change at 50 pascals, yeah, it was possible to find a divide by rule convention that was roughly similar. The most common suspect, divide by 20, was really only viable for the most sheltered of locations with this particular model. The comparisons hint that those who would like to use the divide by convention, well, they should have a suite of divide by options that are brought into play depending on the wind exposure of the building site. In general, annual patterns were reflected in the May week with the moderate to low wind speeds. However, the comparisons of winter and windy conditions showed that divide by conventions are far more difficult to argue for. And the distribution of infiltration is sensitive to changes in wind direction. The windward side of buildings will often have rooms with rather more than the nominal infiltration rate, and conversely, leeward rooms will be dominated by exfiltration and the movement of air into them from adjacent spaces that happen to have higher pressures.